Hey everyone, welcome back. We are working on section 6.2 and 6.3 in this video. We're going to cover both. They're not very long. So we're going to do applications, and I'm actually going to skip the standardizing a normal random variable because our calculators make it in such a way that we don't need to standardize anything, but we could if we wanted to. So now what we did in the previous section was we assumed everything was standard normal, and now we're going to actually do some applications where things aren't standard normal, but we can still use our calculators to do this. Assume a drive-through times at a local burger place are normally distributed with the mean time spent in the drive-through 138.5 seconds and a standard deviation of 29 seconds. Part A. What is the probability that a randomly selected car will get through the drive-through in less than 100 seconds? Let's draw a picture. So these are in seconds. Right in the middle is the 138.5. And we want to know the probability that a car will get through in less than 100 seconds. Well, 100 is to the left of the 138.5, and less than is shaded like this. So this is 100 down here. Well, this is going to be normal CDF. But now it's a little bit different. So I'm going from negative 999, big number, negative infinity, to 100. And this time, I have to include the mean in the standard deviation, which is 29 seconds. So if you have a TI-84, the interface, the top one will say the lower, and that'll be negative 99999. Then the upper is going to be the 130, it's the 100. And then the mean should be 138.5 now. And the standard deviation should be 29. So second distributions, normal CDF, negative, bunch of nines, up to 100. And now I have to put in the 138.5 and the 29. It's a little over 9% chance that you'll get your meal in under 100 seconds. Part B. What is the probability that a randomly selected car will spend more than 160 seconds in the drive-through? Well, let's draw the picture again. Start again. Some of you with iPads are laughing at me right now. They're relatively new, seconds. And they want to know more than 160 seconds. So 160 is going to be over here, 160, and more than is over here. So once again, we have normal CDF. We start at 160 is the lower in this case. The upper is positive infinity. And 138.5 and 29. Let's see what we get. Second vars, normal CDF, 160, comma, big number, comma, 138.5, comma, 29. So what's the probability it'll take longer than 160 seconds? Almost 23%. In part C, what proportion of cars spend between 2 and 3 minutes in the drive-through? Now, this is a little tricky. We need to keep in mind that 2 minutes, since everything's in seconds, is 120 seconds to 180 seconds. We have to translate that. Let's see what we get. So part C. And this is in seconds. Middle's 138.5 seconds. And 120 seconds is over here somewhere. 180 seconds is over here somewhere. So that is what we are looking for. It's not inverse, this is just normal CDF. And this one doesn't have an infinity. This is from 120 to 180, 138.5, and 29. All right, second vars, normal CDF, 120, comma, 180, comma, 138.5, comma, 29. Again, if you have the different interface with the TI-84, you should not be using any commas at all. So a pretty darn good chance, I would say, of between 2 and 3 minutes. 6620 is what I'm getting. So this problem was asking for, what's the probability of something? We are now going to go in the other direction with example 12 here. It says find the reading speed, the reading speed of 6th grade students is approximately normal with a mean speed of 125 words per minute and a standard deviation of 24 words per minute. Part A, what is the reading speed of a 6th grader whose reading speed is at the 90th percentile? Let's see what that looks like. So A. Come on. All right. All right, our mean is 125, and this is words per minute. And the 90th percentile is going to represent the bottom 90%. So in this case, we're given the area, and we want to know what this marker over here is on the z-axis, as it were. So this is going to be inverse norm. 0.9. Remember, it's always area to the left, which we have. Oops. But now we have to tell it the standard, the mean and the standard deviation. Let's see what we get. Second vars inverse norm now. 0.9, comma, 125, comma, 24. So that's about 156 words per minute. Now, let's interpret what that means. That means if we find a 6th grader that can read 156 words per minute, then 90% of the other 6th graders read slower than that student does. And this, of course, is 156 on our graph here. Part B. Determine the reading rates of the middle 95% of all 6th graders. What are the cutoff points for unusual readers, both slow and fast? So what we're going to have here .25. Again, this is words per minute. And they want the middle 95%. Now, this creates a small problem for us because we now need to know how much area is in the blue as well. Well, that's not a problem. If 95% is in the middle, that means what we're missing is 5%. And half of 5% is 0.025. So that's how much is in here. which means we have to do this twice. So inverse norm. Now the first one here is very easy, 0.025 at the mean 125, standard deviation of 24. So this is going to be inverse norm 0.025, comma 125, comma 24. So about 78 words per minute. So let's put that down here. 78. Now, how much area is to the left of the other one? Well, that's going to be 1 minus 0.025. Or you could add the two up and get 0.975. Both are correct. Let's see what we get for that second inverse norm. 1 minus 0.025, 125, 24. To 172, 172. We have two answers in this case, and I want to make sure that we can interpret this. So if we find a sixth grader that reads slower than 78 words per minute, then that's unusually slow for a sixth grader relative to this group that we have. If we find a sixth grader that can read more than 172 words per minute, then that sixth grader is unusually fast. All right, part C, find the 20th percentile. Part C. 20th percentile, as we've been doing with percentiles. I don't have to do 125. 20th percentile is going to be the cutoff point where 20% of the students are slower than this cutoff point. This again is inverse norm. Oops. 125 and 24 again. Again, this is in words. All right, second inverse norm. 2, comma 125. It's about 105. And let's interpret this. A student that can, a sixth grade student that can read 105 words per minute, that is the cutoff point to where 20% of the other sixth grade students read slower than this particular student. In part D, it says find the third quartile. So part D, Q sub 3, which is P sub 75, if you remember. Meaning 75% of the data is below the point that we're looking for. And so 75 cutoff point is going to be over here. And we're looking for that cutoff point there. About 141. It's not too bad. I mentioned that we are going to keep going with this video. Part 3 is the central limit theorem. Regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size n increases. That is the central limit theorem itself. Let's talk about what this means. Let's say that we are in a large stadium and we find out that the average height of the people in the stadium is 5'4", and we with a standard deviation, and we randomly select someone, and that person is 6'6". Well, we've met people that are 6'6" before. We know that they exist, so it's not that weird if we find one person who is. But what would be weird is if we selected 5 people at random from the same crowd and their average height was 6'6". That's more unusual. Meaning, the larger the sample, the smaller the standard deviation has to become. And so we end up with, I'm trying to cut through a lot of what all this is saying. Here are the highlights. Our standard deviation has to be divided by the square root of the sample size. A couple of important things here. The shape of the distribution of the population dictates the size of the sample required for the distribution of the sample to be normal. If the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal over a large size, meaning n needs to be bigger than 30. If the distribution population is normal, then the distribution sample mean is normal regardless of the sample size. All right, what does all this mean? Well, this means if we have a sample, we have to adjust our standard deviation. Here we go. Cell phone lifetimes. A recent study of the lifetimes of cell phones found the average is 23.4 months. Let's put that down. That's our X bar. The standard deviation is 5.2 months. If a company provides its 33 employees, here's our N, 33, with a cell phone, find the probability that the mean lifetime of these cell phones will be less than 23.8 months. Assume that the cell phone life is normally distributed and so on. All right, so what does this mean for us? Well, when we draw our picture, in the middle here is our mu. I should correct this. This is not X bar. This is mu's of X bar. Meaning if we do these sampling over and over and over and over and over again and get an average of each of the samples, what is the average of the averages? Meaning that becomes normally distributed, which in this case is the 23.4. And this is in months. And what we're going to do is we want to know less than 23.8. So let's be less than 23.8 months. So 23.8 is just barely going to be over here. And we're going to find this probability, which means we're going to be using normal CDF. So we're going to go from negative infinity to the 23.8, pardon me. Our mean is 23.4. Now our standard deviation is going to change because we have a sample. And in this case, the sample is the 33 employees. So we're going to end up doing, you can see the standard deviation up top there, is going to be, our standard deviation in this problem is 5.2. But I have to divide that by the square root of n, which in this case is 33. Here's how we put that in. Now, we have to do this whenever there's a sample and we're doing this. So that's what you're looking for in your homework and stuff. Second distributions, normal CDF, negative big number, up to 23.8. The mean is 23.4. The standard deviation, I'm going to put it directly in 5.2 divided by the square root of 33. There it is. 0.6707. Again, because we have a sample of 33 employees in this case, our standard deviation gets hit. We have to divide out the square root of that. All right. A survey found that the American family generates an average of 17.2 pounds of glass garbage each year. Assume the standard deviation of the distribution is 2.5 pounds. Find the probability that the mean of a sample of 56 families, so there's the sample again, that's the indicator that we're going to be using the central limit theorem here, will be between 17 and 19 pounds, and assume everything is going okay. So let's draw a picture. And this is pounds of glass. In the middle here, we have 17.2. And they want to know between 17 and 19 with the sample. So we're just going to change our standard deviation. So normal CDF, start at 17, go up to 19. Our mean is 17.2. And our standard deviation, again, is going to be 2.5 divided by the square root of the 56 families. Second distribution, normal CDF, 17, 19, 17.2, the mean, and then 2.5 divided by second square root of 56. We get this value here, a little over 72%, about 72.5%. We have to adjust the standard deviation. All right, and this last one is a good example of showing how things change because it's the same problem except the sample size just gets bigger. Suppose a geyser has a mean time between eruptions of 94 minutes. Let the interval of time between eruptions be normally distributed with a standard deviation of 27 minutes. Part A. What is the probability that a randomly selected time interval erupts longer than 107 minutes? Now, the key to this one, where we're not really going to be using the central limit theorem, is it's just one of them. So this is going to be the probability that x is bigger than 107 minutes. Well, that's just normal CDF of 107, infinity, a big number. The mean is 94 minutes. The standard deviation in this case is just 27. Don't need to sweat. You could divide by square root of 1. You'll get the same thing. Normal CDF. 107. Big number. 94 and 27. Okay. A 31.5% chance. That it will take longer to erupt than 107 minutes. However, for part B, they want to know what's the probability of the random sample of 8. Now we have an N, a random sample of 8 time intervals between eruptions, has a mean longer than 107 minutes. So this is X bar is bigger than 107. That's normal. CDF 107 to infinity. The mean is 94, but now the standard deviation is 27 divided by the square root of 8. And this is going to change the answer. And you'll notice it's still 107 to infinity, but this is a dramatically different answer. Now, part C has an even larger sample size. What is the probability that a random sample of 29 time intervals between eruptions has a mean longer than 107 minutes? This is going to go down significantly, I'm guessing. Everything else is the same. 27 divided by the square root of 29 now. And notice it went down even further this time. I hope you found this helpful.